Good morning, everybody. Today's class will start up with the Blingh's creep theory, that is used for the design of impervious floor for subsurface flow. Here you can see this is any structure which is being built. Over here the water is going to percolate along the subsurface of the structure. So how to design a impervious floor to avoid this flow? So this is about Blingh's creep theory. Here Bligh made some of the assumption under that. The first one is the percolation of water. It is going to creep along the base of the structure which is in contact with the subsoil. See here in this one the flow without a vertical cutoff. We are not providing any vertical cutoff. In this one the water is going to creep along the length of this. So here this length, that is the path where the water is going to percolate, that path is called as creep length. Here if I want to find out what is L, that will be your overall distance, that is this L. For the next one with a vertical cutoffs, here the water is going to percolate along with the cutoff, that is along with the distance D1, and then move along with the length, overall length of the base, and then D2. So here if I want to find out what is the creep length for this structure will be 2 times of D1, because here it is a downward movement, again it is an upward movement. So 2 times D1 plus along the length it is flowing, so plus L plus 2 times the D2. This will give you the creep length. And another one assumption he made, that is hydraulic gradient is constant throughout the percolating pattern. Here hydraulic gradient is nothing but the head loss per unit length. Next, the similar way will go for 3 vertical cutoffs under the structure. So here what I have explained the same thing. Bligh assumed that the percolating water creep along the base of the structure which is in contact with the subsoil. The length of the path thus traversed by the percolating water is known as creep length. Bligh further assumed that the head loss per unit length of the creep is hydraulic gradient, and this one is constant throughout the percolating passage. Thus the head loss is proportional to the length of the creep. Bligh made no distinguish between the vertical and horizontal creep. This one, so this downward direction, that is called as vertical creep, and horizontal movement of water, that is called as horizontal creep. So here you can see this H by L 2 times of D1, that is if you consider as an hydraulic gradient. So the same thing at this point, it will be same, but depending upon the length of the cutoff, that is D2, and here it will be H by L times of 2 times of D3, that is hydraulic gradient for this point. So he has considered for all over the length of the structure the hydraulic gradient will be constant. So for this diagram, considering a barrier impeding the water depth, that is H, this is a barrier which is provided with horizontal floor of base B, that is length, that is B, with 3 vertical cutoffs. Here for 3 vertical cutoffs, if I want to know what is the creep length, it will be L is equal to 2 times of D1 plus overall length, that is we have considered B, so it will be 2 times of D1 plus B plus 2 times of D2 plus 2 times of D3. That will be the creep length. So here you have got creep length is equal to L is equal to 2D1 plus B plus 2D2 plus 2D3. And then hydraulic gradient is nothing but the ratio, that is ratio of H by L. So Blingh has assumed that hydraulic gradient will be constant. So here we have considered H divided by 2D1 plus B plus 2D2 plus D3. This is nothing but creep length. And here the reciprocal of hydraulic gradient L by H is known as Blingh's creep coefficient, that is C. So here if I want to know what is L, so it will be L is equal to C times of H, where C is in Blingh's coefficient. Next we go for, if we have designed this impervious floor, next we have to find out is this impervious floor is safe against the failures. So here there are different types of failures. Considering those, we have to find out the safety. Is it satisfying to ensure the safety against the failures? Here, according to the Blingh, the following criteria are being satisfied to ensure safety of impervious floor against failure. Under that, first one is safety against piping. Here, the length of the creep should be sufficient to provide a safety hydraulic gradient according to the type of the soil. So, the value of C, that is Blingh's creep coefficient, is going to vary with respect to the type of the soil. If the soil type under the structure is coarse graded soil, then the value of C is 12. If it is sand mixed with a boulder and gravel, the value of C is 5 to 9. In the worst case, giving the maximum value of H should be selected for the design. Here the maximum seepage head occurs when the water is at highest possible level and no discharge on the downstream side. Like we are not going to allow the water to pass from the upstream side to the downstream side. In that cases, the maximum seepage head 2 occurs. Next is safety against the uplift pressure. Here the ordinate of the hydraulic gradient line along the bottom of the floor represent a residual seepage head or uplift pressure at the point. So here you can see this one. This is uplift pressure diagram. For this it is this one. So here for uplift pressure exerted by the percolating water is given by W into H dash, where W is nothing but your gamma. Okay, here I have represented as the W. Okay, into H dash. If T is the thickness of the floor at the point and G is a specific gravity of the material which is used for the construction of the floor, then the weight of the floor is given by gamma G into T. For an equilibrium, the uplift pressure must be counterbalanced by the weight of the floor. So gamma H dash is equal to gamma G into T. So we can find out what is T, that is thickness of the floor. So T is equal to H dash divided by G, where your G is nothing but a specific gravity, and ordinate H dash of an hydraulic gradient line is from the bottom of the floor. Here, if I want to know what is H dash, this I'll consider some point on this hydraulic gradient line. This one is H dash. So this distance is taken from the bottom of the structure. Okay, this is the height. Next, same thing, I'll do a thing. I want to know what is H dash. H dash is equal to what? G into T. So G into T. I'll take this one to LHS. So it will become H dash minus T. N is equal to T into G minus T. See why I have considered T again. If we have taken common and it get cancels, nothing is going to change. So the overall T value will be H divided by G minus 1. This is how I got H. That is, H is nothing but, if I want H, so H dash minus T. This one overall is H dash. This is T, that is thickness. If I want to know what is this height, it will be H dash overall distance, that is overall height minus this thickness, that is H dash minus T. You will get this height, that is small h. Okay, that is how I got in this equation. Fine. So I can say H is nothing but an ordinate of hydraulic gradient line measured from the top of the floor. Here, considering a factor of safety of about 4/3, so your thickness will be T is equal to 4/3 into H divided by G minus 1. So this is about factors which is going to work against the failures. So we have to take care of that one before designing of the subsurface. Next we go for limitation. Here first and foremost is Blingh has made no distinguish between the horizontal and vertical creep. That is the moment of percolation of water. Next is the Blingh method holds good as long as the horizontal distance between the cutoff or piles is greater than its depth. If it is less, then it is not going to hold good. Next is Blingh made no distinguish between the effectiveness of the outer and inner face of the sheet piles. However, the outer face of the end sheet pile are much more effective than the inner ones. And Blingh made no distinguish between the short and long intermittent piles, and these piles of length shorter than the outer ones are ineffective. See here, this one is longer and this one is shorter. So this is ineffective. Next is, according to the Blingh, the loss of head, that is hydraulic gradient, is proportional to the creep length, but it is not true. Also, the actual uplift pressure distribution is not linear, but it follows a sine curve. And Blingh did not explain the absolute necessity of providing a cutoff at the downstream end of the floor. However, It is absolutely essential to provide a deep vertical cutoff at the downstream end of the floor for preventing the piping failure. To overcome all this, there was another theory came across, that was Lane's weighted creep theory. This is nothing but an modification of Bligh's creep theory. Only thing what he has done is he has given a weightage factor for the horizontal creep and as well as a vertical creep. Here, the Lane approached the problem by making an statistical examination of 290 existing structure on the on pervious foundation and evolved a theory in 1932, which is known as Lane's weighted creep theory. Lane made no distinguish between horizontal and vertical creep as well as Blingh made. Here, Lane indicated that the horizontal creep is less effective in reducing the uplift than the vertical creep. So here he has proposed a weightage factor of 1/3 of a horizontal creep as against 1 for a vertical creep. To ensure the safety against piping, LW, it should not be less than C1 of H. This is your creep length and it should not be less than C1 of H. C1 is nothing but the Lane's weighted coefficient of creep and H is an hydraulic, this one, hydraulic head or head loss. Again, C value is going to vary with different types of soil. For fine sand or silt, here the C1 value will be 8.5 and for fine sand it is 7 and for the coarse sand the value of C1 is 5 and the value of C1 is 3 to 3.5 for gravel and sand. For boulders gravel, the C1 value will be 2.5 to 3 and for clay soil it is 1.6 to 3. This is about Bligh's creep theory and Lane's weighted creep theory. Next we go for a problem, a simple problem on Bligh creep theory. Here the figure shows, this one shows the section of an hydraulic structure founded on sand. Calculate the average hydraulic gradient. Also find the uplift pressure at 6 meter, 12 meter, 18 meter from the upstream end of the floor and find the thickness of the floors at each point. So this is your H and this is your thickness. Here we have to find out the uplift pressure at this point and this point and this point. So this is 8 meter, this thickness is 6 meter. First one will go for the length of the creep. So here length of the creep is L is equal to 2 times this distance, that is 6 plus overall length, that is 22 plus 2 into 8 meters. So how the water is going to percolate, that length is 50 meters. Next, hydraulic gradient. Hydraulic gradient is H divided by L. So this is nothing but this height, that is 2 meter divided by L is length of the creep. So 2 divided by 50, that is nothing but 1 divided by 25. Next, In the problem, they have asked us to calculate what is the uplift pressure up to the point A, up to the point B, and up to the point C. So we'll start up with the point A. Here the length of the creep at the point A is nothing but the downward moment of with the distance 6 plus upward moment with this along the cutoff, that is 6 plus 6, or you can also write it as 2 times of this height, 2 times of 6 plus the length up to the point A, that is 6. So overall it will be 18. Overall it will be 18. Next we have to find out what is H, that is unbalanced height. So for that we have to take overall this height, that is H, minus of overall length of the hydraulic gradient, that is 1 divided by 25. So 2 minus 1 divided by 25. So it is acting along the length of the creep, that is 18. At the point A, if I want the unbalanced head, so that will be, I'll be considering it as H1. For B it is H2. For C it is H3. Okay. So unbalanced head, it will be 1.28. Now we have to find out the thickness of the floor at A, considering the safety against the uplift, that is T is equal to 4 by 3 times of H divided by 2.4 minus 1. This 2.4 is nothing but G. Okay, specific gravity of the material. And this height for point A, it is H1. So your thickness is 4 divided by 3 into 1.28 divided by 2.4 minus 1. It will be 1.22. So for the point A, the thickness will be 1.22 meter. Next we go for the calculation of thickness of the floor at B point. For that, again same thing. This remains constant, correct? No? Total length of the creep, it will be constant, and hydraulic gradient also it will be remaining constant. Only thing it is going to vary is, now I have to find out the length of the creep up to the point B, and H2, that is unbalanced head, it is going to vary, and finally the thickness is going to vary. Fine. So for the point B, the length of the creep up to the point B is 2 times of 6, that is this one, and then overall length. So overall length up to the point B is 12, so plus 12. So it will be 24. Next, the unbalanced head is again 2 times of this distance, that is head, 2 minus 1 by 25, that is hydraulic gradient, into the creep distance, that is creep length, that is 24. So unbalanced head will be 1.04 meter for the point B. Now we have to find out what is our thickness. So thickness is equal to 4 by 3 times of 1.04, that is unbalanced head, divided by specific gravity of the material, that is 2.4 minus 1. So approximately you will be getting around 0.99 meter. It will be rounded off to 1 meter. So for the B point, your thickness will be this one. This height will be 1 meter. Next, for the point C, similar way. So your creep length will be 2 times the 6, that is this, plus overall length, that is 18. So it will be 30, and your unbalanced height will be 2 minus 1 over 25 into the overall creep length, it is 30. So your unbalanced height will be 0.8 meter. Using this one, we have to find out the thickness. So your thickness will be coming around 0.76 meter approximately. We are going to round it off to 0.8 meter. So this is about Blingh's creep theory and Lane's weighted creep theory. So today's question is, what is a weightage factor for the horizontal creep which is being induced by Lane? In tomorrow's class, we'll start up with the Kosla's theory, that is an end of the module 3.